Well, good afternoon, everyone, and welcome back to the last in this April Bite-Sized Corrosion series, where we've been talking about material selection. Now, in this series that we've been looking at some material selection, we started by embarking on a discussion with Neil Webb, looking at some of the key factors or key considerations that we should take into account when we choose materials. Now, obviously, mechanical properties are right up there as very important. We also saw the relevance of looking at the environment in which our structure is going to be used, because that will have a significant contribution to what material we choose, because we might have conditions that require something special. Now, last week, we spent some time with Donovan Slade, and we spoke about the added value that we could get in our material selection by using a complex polymer such as polyurethanes to provide, for example, corrosion resistance when the operating parameters might make conventional steels impractical or fancy steels too expensive. It was a really interesting discussion, and I encourage you to watch the video if you missed it. Now, today we're going to take this a little further, because sometimes polymers themselves are not enough. And really today I'm delighted to welcome Louis Pretorius to the microphone to take us a little bit further as we dip our toes into some even more advanced materials. Now, who is Louis? Well, Louis studied mechanical engineering here in South Africa and spent a few years working on power stations, where a serendipitous encounter with a leaking butterfly valve resulted in him making contact with Coracoat for a suitable solution. And in a sense, the rest is history, because Louis is now, after about 30 years with Coracoat, now the MD of Coracoat in South Africa. Not just a pretty face, Louis also spent some further time in the UK studying corrosion and polymer chemistry. So he's added extensively to his practical knowledge. And Louis, I know you call yourself a fixer by nature, so you're definitely the right person today to chat with. So a warm welcome.
Vanessa, thank you very much for that welcome and for reminding me about the origins of how my career in corrosion protection started off in South Africa. So thanks for that reminder.
Louis, last week we spoke about using polymers to give us some corrosion resistance, but they don't always work. Is there something else we can do to our polymers to make them work a bit better?
Vanessa, yes, there is, and it's an area of specialization that I've been involved with for most of my working career. If you look at the polymers, we normally think that coatings performance is based on the chemical resistance or temperature resistance or adhesion of the polymer, and be that a polyurethane, as was discussed last week, or epoxies, which are the most common materials, or polyesters and vinyl esters, which we use in the fiberglass or the composite type industry, or a host of other materials that we have. So once you have the chemical resistance, you then have to ask yourself, how else can I change the mechanical properties of that coating or resin system? And one of the issues that we found was the failure mechanisms. And generally, the failure mechanisms would be osmotic blistering, a loss of adhesion over time. So if you put on a new coating, it sticks very well, and you leave it immersed in water for a couple of years, you find that the adhesion reduces. And further studies indicated that a lot of this had as its root cause permeation of small molecules such as water or oxygen through the coating film. And it was this awareness that the permeability of polymers or coatings contributes to their mechanical properties, and then also contributes to the characteristics of the formulated coating once it is applied to a steel or concrete substrate to offer corrosion protection. So there's some basic ways in which we can increase the permeation resistance of a coating. And the most common one is just make it thicker. If the coating is thicker, it takes a longer time for a water molecule or an oxygen molecule to diffuse through that coating. The second way is to improve the cross-linking density. So last week we had some discussions on the chemistry, and the cross-linking density relates to how well the material cures or polymerizes, and how well the individual chains link to each other, and how many truly minute size, how many interstitial spaces are there between the molecules and the polymer chains that comprise your coating system. One of the ways in which we can improve the properties is by adding fillers such as flakes. These flakes started off as being added as colored pigments, and then they became a whole industry with the area of specialization by themselves. So you can add the flakes to a host of different materials to slow down the diffusion of small molecules through those materials. So I hope that helps, Vanessa.
Thanks, Louis. I think my first response is then the painter who puts on a thicker coating, he can have some logic there, but as we know from our various coating discussions, the thicker isn't always better. But you're talking about flakes, and I presume you're not meaning cornflakes. So what flakes would we add to our coating to make it less permeable?
Cornflakes generally work very well with milk, and they work very well with polymer resins. Okay. The most common flakes that are used are the glass flakes. There are other types of flakes, such as mica, micaceous iron oxide is another type of common flake, but the ones that perform the best by far are the glass flakes. They're like orders of magnitude better in reinforcing these coating materials. And while they might primarily be added to reduce the rate of diffusion through the polymer film, they can also be added to impart a lot of other properties, mechanical properties to the polymer or the coating.
And what sort of sizes are we looking at? Again, I tend to think on a more macro scale. So flakes, to me, I'm thinking shards of glass, but that's obviously too big. So how big are these glass flakes?
Well, visually, they would range from talcum powder, absolutely talcum powder, to something that looks like glitter, okay? And that the kids play with, or that you may find in certain cosmetic products or paint products. Those are the size of the flakes. Now, practically, you would start with flakes maybe 3 or 4 millimeters in a rough diameter, because they're not perfectly round. They have an irregular or angular shape, and they may be 10 microns thick. And then you come down, you could have flakes that are 1 millimeter diameter, 500 nanometers in diameter, 200 in diameter. And the same with the thicknesses. So you could have flakes that are ranging typically 10 microns, 7, 5, 3, 2, 1 microns, and then they go submicronic in their thicknesses. So again, you could have 700, 500, 250, 100 microns. And the limit to the technology currently is around 75 nanometers in thickness. And we can do consistent production runs where you're making 75 nanometer thick flake, and you're making several tons of it in a batch.
That's really small. Louis, you spoke about flakes, and I can understand, again, because I think on a more macro scale, that they could either orientate sort of, an uneven way, or perhaps more layered structure. Can you control their orientation, and what is the best orientation that you would want within your resin?
Good question, Vanessa, because the addition of flakes, it means that we're going to change the properties of the material, and we must orientate the flakes all parallel to each other and parallel to the substrate. So if we don't get the flakes predominantly parallel to the substrate and to each other, the whole system of flake-filled resins or coatings just stops working, doesn't work properly. So that aspect is critical.
So I've got a couple of slides. Thanks, Louis. And I think this one really just shows the permeation challenge.
If you could conceptualize an oxygen molecule or a water molecule, which are two of the common ones that would drive corrosion cells, you could see that they're going to go through that 3-coat system and eventually get to the steel substrate. But when we have oxygen and water at the steel substrate, we know as corrosion engineers that you could be having corrosion cells arising, and we want to stop that or slow that down as much as we can. So you could immediately see there that if you had a 5-coat system where you added 2 extra layers to that, you increased the total thickness, and you would then also take a longer time for the oxygen and water vapor molecules to get down to the surface. When we add flakes to a polymer or to a coating systems, the flakes need to orientate similar to how they're on that schematic, so that we create a long path length. And this is the principle of the tortuous path. And the principle of tortuous path is important for all the different users and manufacturers of flake-filled resin systems around the world. You can imagine them as little fish scales. And if you can put in 100 layers of fish scale in 500 microns or in a millimeter of coating thickness, you can imagine that the barrier properties of that barrier against diffusion is substantially higher than the identical resin system or coating without flakes.
The additive, yeah,
so
that makes a lot of sense.
Quite often we compare the performance of the resin system without flake at a given thickness to the diffusion or the permeation resistance of the resin system with flakes. And then once you compare those two, you'll see that there's like orders of magnitude improvement in permeation resistance or slowing down of the rates of diffusion. So what we're looking at there is some flake-filled coating, and just a little bit of background on how we make that. We have the privilege of owning 2 electron microscopes. So what you do is you take the coating and you freeze it with liquid nitrogen, and then you shatter it, and then you mount it like that without polishing it. That's how we get these photographs. And superimposed upon there, the red lines that you're looking at there are possible diffusion paths for a water molecule or an oxygen molecule or some chemical like hydrochloric acid or hydrogen sulfide. So all the small molecules would diffuse through that easier, while something like phosphoric acid or sulfuric acid, which might be strong acids, would be relatively large molecular sizes. So what you see there is actually a thin layer of resin gluing the flakes together. And the way the small molecules diffuse or permeate is only through the resin. They don't go through the glass.
Essentially, we're putting in a glass layer and we're holding it there with resin. It's not solid glass, but that's effectively what we're doing.
Absolutely, Vanessa. So we've glued in 100 layers of flake or more, and that's given us the diffusion time, and that path length ultimately gives us life expectancy. Because if it takes a longer time period for a water molecule, something innocuous, to diffuse through the coating, it just means that the coating is going to last so much longer. And that's why the glass flake coatings under very arduous lab test conditions tend to outperform the same resin system that is unreinforced.
Yes, I think that was really helpful. And for someone like myself who doesn't have much experience in reading micrographs, it's really helpful to have the red lines there to show me where I'm looking. Okay, so now we've essentially got this glass layer held there. So the benefit is it gives us this very long path, but what are the trade-offs? What can we end up losing when we specify a glass flake or a reinforced polymer?
That's a good question, Vanessa. There's multiple answers to that. These flakes come in a variety of sizes in nominal or rough diameter as well as thicknesses. Mm-hmm. And by blending the correct size flakes with your resin polymer to make your coating, you can then impart different properties. So for argument's sake, flexibility, if I wanted to make a flexible glass flake coating, I'm going to use very thin flakes with a very small diameter. While if I was interested in improving abrasion resistance or wear resistance, because I've got a lot of sand and silt in my water, or I'm getting high velocity jetting and erosion and abrasion, I go for very large flakes that are quite thick, so that they have more structural strength. When you start looking at the size of the flake relative to the properties that you want to change, the mechanical properties that you want to change in your resin system that holds your coating together, you can start to modify these things. And then likewise, if I wanted impact resistance, because I've got a conveyor that's throwing stuff into a chute, you may want to go for little nano flakes because they would deal with the impact very well. Or alternatively, you may want to make them very thick and strong and make the flakes not out of glass, but you may want to make the flakes out of silicon carbide or silicate alumina. So you still have the principle of platelets or flakes in your resin system, but you're now better able to deal with the impact or the abrasion, depending on what the application is. And then just some notes tying into what you were saying about the types of flake. If you have a solvent-based coating, okay, you can't put a lot of flake into it because the solvent needs to come out, which would then be the reverse path length to how you're trying to stop the oxygen or the water getting down to the steel substrate. So solvent-based coatings generally as a guideline have got quite low levels of flake. They might only have 3 or 5 or 7% flake in it, while the 100% solids coatings or the solvent-free coatings could have much higher levels of flake loading because they're not going to solvent entrap. The last point, which is important, I think, is to also consider the chemical resistance of the flakes themselves. So the glass flake coatings often get put into very aggressive chemical service. They might be in sour crude, they may be in mining applications where we got alkaline leach or acid leach. And to do that properly, you then need different grades and types of glass. So as a company, we're very privileged to own a dozen glass melt reactors scattered around the globe where we make molten glass. And then you take the molten glass, which looks like lava, and you put it through a patented process. And then you make these little flakes. And by changing the process, you can then also change the size of the little flakes that you produce. But it gives us the opportunity to then also make flakes with varying chemical resistance. So they may be more optimized for acid environments. They may be optimized for hot water or hot gas environments, hot demineralized water, or they may be optimized for alkaline environments, because strong alkaline environments tend to dissolve common glasses. So the types of glasses typically would be E-glass, which is the electrically insulative glass, or C-glass, which is corrosion resistant, or ECR, which is extra corrosion resistant, or Advantex, or secret formulations of glass. And just like various coating manufacturers guard their recipes, their cake recipes for making gee-whiz coatings, and so we have different formulations for making different types of glass for different environments.
So you've just added a further level of complexity to the selection of the right product, because now we're worrying about the glass itself. Louis, a lot of the examples that you've alluded to have been applications where it would be kind of within a vessel. Are there any applications, or is there a use of glass flake material where it's exposed to sunlight? You did mention one of a conveyor. Glass shouldn't react negatively with the sun, but I would guess that the resin itself would need to have some sort of UV resistance.
Correct, Vanessa. So you can use glass flake coatings in atmospheric corrosion. They tend to use them offshore where there's a lot of salt spray, or where items are in mist belts, if they're onshore and they're in mist belts. They also get used in process plants where there's very strong chemical fumes, and you need another level of protection from your paint or your coating system. And the glass itself is pretty impervious to ultraviolet light. It's not bothered by ultraviolet light. But what it does is glass generally has reflection, refraction, and diffusion properties when subject to light. And it has one other benefit in that it protects the underlying resin binder. Now, that is less important if you're using unsaturated esters like isophthalics, bisphenols, polyesters, or vinyl esters. But if you're using a common material such as an epoxy, we know that epoxies tend to chalk. And the chalking rates of epoxy might be anywhere between 5 and 20 or 30 microns a year, depending on the formulation of the epoxy, but they all chalk. If you go and add the little glass flakes, what happens is it only chalks in the surface layer. So it might chalk down one layer, maybe 2 layers, and then thereafter the chalking stops because it's a surface effect. So we've traditionally protected epoxies by adding coatable polyurethanes or polysiloxanes, which are more color stable in recent years, is how we've protected epoxies. But another way of protecting them is you can add the little glass flakes. Initially, the color will be quite bright, and after a year or two, you might find that it looks a little bit glittery on its surface because you've lost 10 or 20 microns of resin on the surface, and now you're exposing the top side of the glass flake, and the bottom side of the glass flake is still glued to the epoxy and still protecting the underlying epoxy.
And Louis, just thinking about this, we've got all this glass now in our coating. It's a stupid question, but is it going to crack? And half of me says no, because you've got flakes, not a sheet of glass. But it's a question I'm going to ask.
Vanessa, it's a good question, and I get asked that question quite regularly. So no, it doesn't increase the tendency to crack unless we were formulating coating system for wear and abrasion and we had very large flakes in it. But if we have the medium-sized flakes or the fine flakes or the nano flakes in there, it actually slows down crack propagation and prevents crack propagation.
Yes.
Part of it is it helps with distributing the shock. So it distributes the stresses over a larger area, it doesn't give you point loading, okay? And then it stops the crack propagation paths as well. So like materials, there are limits, and if you hit it with a sledgehammer, you're probably going to crack it. But generally, blunt force doesn't cause cracking of these materials. You actually need a sharp point, like a chisel. Right. And even if you do crack it or chip it, okay, so it's not just cracks, it's chip it. What happens is it doesn't chip down to the substrate. It only knocks a few flakes off the surface, and you then still left with an underlying layer that can still pass a spark test and still insulate the substrate from the corrosive environment.
These are not usually products that one can just request kind of almost off the shelf. You'd probably have to do a bit of R&D to find the right solution for your particular problem. Would I be correct in that? Absolutely,
Vanessa. So if we look at how much flake to add to a coating, is it 1%, 5%, 10, 20, 30, 40% flake that you add to a coating? In the old days, we used to believe that saturating the coating or adding flake up to its critical pigment value, CPV, in which it just wouldn't absorb more flake, would give us the best level of permeation resistance. But R&D found that that's not true, and you have to actually make up the samples, do the tests, do the work to find out what is the optimum flake loading. So for solvent-based materials, it could be right down at the bottom end of the range, maybe 3, 5, max 7% of flake. For 100% solids materials, you find that it's anywhere between sort of 10 and 25% flake loading would give you the optimum resistance to diffusion or permeation. For practical purposes, when we do these tests or the batches, changing the flake concentration by 0.5% or 1% may move it away from its optimum loading, which is a very narrow range or band to find the optimum loading for your particular resin system. So yes, you must do R&D if you want to have flake-filled coatings. They're definitely not all the same.
Well, Louis, thank you. You've given us so much food for thought. Thank you so much for taking time out today to be with us and for helping me to appreciate flakes and flake-filled materials a little bit more. And I'm sure our audience would also agree that this has been really informative and educational. So thank you.